although it's a review of the last week's, however, thank you. It's a good one. So that was also uh, another good example of the control system. For that case, it's a position control. Theta angle is controlled. So rotation angle is controlled. That's the example we talked. That is translational motion. So linear motion, in other words, is another type of action, and control the position of it. That was simple hybrid electric vehicle operation. We talked that I spent more time on this one since it is one of the most sophisticated control system in the future. Electric cars are going to be autonomous without any driver. Therefore, we have to understand the control concepts of it. Production system we discussed. That one is the first prototype in your lab. Then when you test those, you can see that there's a feedback here. And however, at the end, when you reach the product, you always compare it with the recent developments of the market demand. That is also another control problem. And we have also discussed the linear system and nonlinear systems. We have seen that in mathematical wise, the function which cross zero with a constant slope, that one, can you see that, is linear. That is line, however, but it is not mathematical wise linear, since it's not crossing zero, okay? Although that one is crossing zero, but is nonlinear. And also that one is crossing zero, but it is nonlinear. Okay, so crossing zero doesn't mean it's not enough, but necessary. Okay, and also linear time invariant. What linear time invariant is all about? Linear time varying is all about. I'm going to explain it to you. Okay, I will come back to linear and time variant and time invariant systems later. Bu önemli çocuklar. That's important. We have several types of inputs to our control system. One of them is a step. So you are actually producing a force which continues. However, if you give a pulse with at an instant, that is impulse function. That is not shown here. However, if your force has got a slope with constant a and is a linear line, then it's a ramp function. Parabolic function is the square of this one, time, and also sinusoidal function you are going to see, particularly you are electric students, electric and mechatronics students, you might be able to see the sinusoidal response of your system to your sinusoidal systems. So this is just revision of last week. Inner loop, outer loop. There are two methods, transfer function approach and state space approach. We are going to use transfer function approach. Transfer function approach use S domain calculations. What's the practical point of the S domain? We have only 6 students in our classroom. That means these students are keen to listen the course early in the morning. They don't want to lose the time, or they don't want to lose some kind of teaching material. So I hope you are going to answer this question. What is the benefit of S domain? what is the benefit of S domain or Laplace converted forms of the equations? What's the benefit? If you don't answer this question, that means you allow us to use Laplace to solve our problem. All right, but what is the benefit? Adil Adel Bayraktar saying that it gives us to solve the problem. All right, how? You see, I also reviewed the Laplace equations, and also it's already in your OLearn system. I also upload that Professor Nick's um chapter on this one. You can see that no matter whether your differential equation has got a second derivative, third derivative, fourth derivative, particularly in electric circuits we involve with the second derivative equations, it all of a sudden with the conversion of the Laplace it becomes algebraic. Okay, so you get rid of the derivations. Anlaşıldı mı? Is it clear now? Evet. To find the input, then doing the inverse of the. No, first of all, you see, you couldn't catch my question. What is the benefit? Benefit means what's the advantage? The advantage, if you have derivation in your equation, differential equation, you convert it to Laplace, make it linear algebraic equation, no derivation. Then, of course, you are going to come back to time domain. S domain is the tool we use. Okay. These are the typical S domain representation of the functions. If it is a unit impulse, it's 1. Step 1 over s. Ramp 1 over s square. Parabolic, if your input is or function is parabolic, 1 over s to power 3. For exponential is 1 over s plus alpha. Of course, alpha is a time constant. Sorry, inverse of the time constant of this equation. Sinusoidal, it's omega over s squared plus omega squared. You don't have to memorize those. You see, during what I believe, the brain is created for thinking and also classifying the knowledge in order to use it if it is necessary, but not to memorize all the equations and things like this. Okay, of course, this is not difficult. This is easy to remind or memorize. But don't forget, if you have a step function, that means it's 1 over s. If it is integral, by the way, it is s. Buraya da geleceğiz. Evet, these are the functions and the theorems of the S domain, particularly final value theorem we are going to use. Bakayım. Pad'i koydum. Bakayım. Pad'le çalışmaya çalışacağım. All right. Final value theorem. Limit time goes to infinite. Error is equal limit s goes to 0 s es. So in order to find the final value, which means ESS, steady state value of the error. What's error? You remember that. This is your control system. This is your input, R. This is your reality. And that one, this one is plus, this one is minus. There's a system here, and that is output. See, these are time functions, by the way, time functions. That is what control system is all about. So that one is plus, that one is minus. So that one is E, error. E is error. I've catch cold. İyi değilim pek çocuklar. Kusura bakmayın bu öksürükler için. So this output minus or input minus output is error. So if you want to steady state error, time goes infinite. But if you want to see in S domain, so you are going to solve this equation. So you are going to convert error time function to S domain, then you are going to multiply with S, and then going to get the limit of it. Okay, this is we are going to widely use this one. We also mentioned about the partial fraction expansion method. You remember that? Olmadı. Hiç hoşlanmadım bu şeyden. Tamam. Partial fraction expansion method. I also reviewed that one, so you can improve yourself. My dear, how many students do I have now? It's 9, I think. 8. Moment. Pardon. Adel, Ahmet, Hamza, Hilal, Halil, Halil Hatim, Mahmud, Ozan, Right. I don't know how to spell it. If you want to improve yourself, I believe that you really think that since you started with me in early time at 9 o'clock, the correct time, of course. If you want to improve yourself, you have to rehearse. You have to solve some problems by yourself and think. If you do not understand, then you ask me. Everything has changed now. Lecturers should not teach simple things. You have to be ready for the engineering life in the future. Therefore, how could you improve yourself? Okay, ask questions to yourself, try to find get the answer, and also organize meetings with your friends as well. Okay, and don't hesitate to ask me. Since I prepared those questions for you, it's not official. It's not official homework, but you have to solve those. Probably, I'm going to solve this one. I'm going to solve this simple one later. Okay. So when you solve those and then obtain the response, then that means you start understanding the mathematics at least of it. So that's the end of last week. We have already discussed. You remember superposition theorem we have discussed. Also, if you have multiple input and system is linear, then you can employ the superposition theorem. Superposition theorem tells you that as if you have each input individually exists and the others equal 0. So you are going to solve it. Göstereyim bir dakika.
Professor, you're on mute.
It automatically mute myself. Therefore, thank you for reminding me. Okay, so this is a system which is linear. So input-output relationship is linear here. However, we have multiple inputs. What we assume that we have the first input alone, so that we put the other input 0, and the second input alone, which obtain the output for this case, but the other inputs are 0, and the third one. Then what we do, actually, this system is equal to those individual outputs. So sum of the individual outputs will give you the total output of the system. This is what superposition theorem is all about. We are going to use it quite often. Okay. So I changed the camera to me. Just a moment, please. Now we are starting this week's course material. Right. So we are going to not only the mathematical modeling, also the introduction to control systems. Today lecture, we are going to move further, move further inside the control systems. You remember this example, but you didn't have that equation here. You didn't have that equation here. The torque which is given to this arm is equal to this one, torque. Torque is a Newton meter, and if you look at the units, it's also energy. This is torque, Newton meter, force times distance. However, since the position is theta, of course, d theta dt reflects the friction. However, the square derivation of the d theta dt, the square second derivation of the theta with respect to t time, is decisive for the stored energy part. So J here is the inertia. So T, however, if you have since this arm is touching here, of course, some kind of load torque is occurring as well. So these are opposing the motion. We assume that our system is rigid. If it is not rigid, then you have to add plus this is also representing the elasticity constant here. B is a friction constant, J is the inertia, and this is a torque load opposing, and the K is the elasticity constant. Elasticity in Turkish burulma. So that one, for if you look at, to me, that one is rigid. However, that rubber, can you see that? That rubber is not rigid, so I can turn the right hand side with respect to the left hand side. So when you leave it, it comes back. So actually, this is also kind of energy storing business. Okay. So this is one well-known equation. You are going to use those equations. In order to solve those equations, as I told you before, in order to solve those equations, you are going to use S domain easily. So this is a second derivation. This is the first derivation. So then you are going to convert it with S square, S involving. Derivation is 1 over S, by the way. Yapacağız daha. You are going to see those. Continue. That is linear motion. So if I make it a little bit, so you can see that for I also add that equation too. So m times mass, in that case mass. In rotating system it was J, the inertia, but for translational motion is the mass. D square x dt square plus b times dx dt plus k times x minus xo. Xo is the original starting point. If system is not rigid, by the way. If it is iron, for example, no, you can't do that. But if it is rubber or any other plastic material, of course you can use that equation as well, representing the torsional effect or motion in translational direction. It's not torsional. Torsional, of course, it's a squeezing or getting longer. Storing energy business anyway, and also the load torque. Load means assume that this is a machine tool. Do you know what machine tool is all about? Takım, in Turkish we call it takım tezgahları. So it's a, for example, drilling a hole here. So drilling force is this one, is FL, drilling force. But of course, in order to drill, system mass, system B, and system K involves. So these are dynamic equation of the mechanical systems. I come back again. So you can see for rotary system is clearly similar. And for that one, that is mass. And also this is friction coefficient. This is spring constant, elasticity constant, and the load force. Force electromechanical is the one produced by electric motor. Electric motor produced those force and overcome all of them. Since there is a balance here, this part is a dynamics of the equation, and that might be steady state. Now, we are now coming back to a simple definitions. Single input, single output system. We have one input, one output. All right. And this is you might call it gain, or you might call it, if it's a complex, transfer function as well. But if you have multiple input, multiple output system, which mainly we are not going to involve those kind of systems, this is called MIMO, multiple input, multiple. You can see that number of inputs we have, and also the controller, the actuator, process, and also the sensor. They all have multiple values. We are not going to use it. What's that one? Is the comparison. We have already discussed that one. A is the value most likely is the your wish. B is the reality, and this is A minus B. That is the definition. RS is your input. CS is your output. Sometimes it's called, some books use YS. Sometimes we use that one as well. Generally, we use CS. However, since Ogata use CS, but other books use YS. So if you see output YS, don't be surprised. Transfer function is CS over RS. That one, this one is important, which is error. Error means how far are you from to reach your objective. Hedefinize varmaktan ne kadar uzaksınız? Error reflects that one. How far are you from your objective? This is a typical closed loop system. Of course, you have a sensor here. That sensor has got also gain. It's called HS. GS, HS. And the transfer function here is equal to, buraya ben yazayım, sonra ya da biraz sonra gelecek karşınıza. Are you following me? Are you with me? I can't see your faces. Okay. Don't leave me alone. Thank you for your responses. Very good. Okay. Now we have, this is a typical control system. The output is, thank you. It's all right. The output is compared with the input. Of course, the measuring device, sensor mainly, has got also a gain. So what's the transfer function of this one? You can derive that transfer function. However, I'm going to put it here, since when I write it like this, you would be remembering that one. TF is equal G over 1 plus G. I'm sorry. Bu kalem bazen böyle yapıyor çocuklar. Bir düğmesi var. There's a knob here. You can see that pen. It's a special pad. That is the pad I use. Okay, and this is the special pen of it. But as long as I put some there is some knob here, and if I make mistake, then it doesn't allow me to write. Look, without touching it. Oh yeah, now it's all right. Önce silelim şunu. Sorry about that. BS is not very important. The book defines as Now what's happening here? Biraz beraber düşünelim. Let's think about this. What's BS? All right, thank you. Biraz incelteceğim kalemi de. Bir saniye. Sabırlı olun. Ha. Okay. BS is equal to CS HS. So that's what happening. CS times HS is equal to BS. However, ES is equal to RS minus BS. So when you calculate CS, the CS over CS, I'm sorry, gene yaptı. Ergonomy is a very important science. Ergonomy. So to make tools useful, for example, the armchair should be useful. That pen is not very good ergonomically. Probably you couldn't see that there's a knob here. By mistake, I put it here and then I lose the control. Anyway, those equations are already defined here. So I come back the same one. All right. Now starting from, follow me carefully. This one is loop transfer function. Is not very important. GS times HS. However, feed forward transfer function is important. Feed forward transfer function. CS over ES, which is equal GS. Tamam mı? CS over ES is feed forward transfer function. However, closed loop transfer function is GS over 1 plus GS HS. Evet. Derive etmemişim. I haven't derived that equation. I haven't derived that equation, transfer function. Now I expect you yourself to try to obtain that one, since it is equal to, this one is equal to yazıyor. Bıktım ya. Elimle yazarım daha iyi. I can also write by using mouse. That one TS transfer function, which is equal CS over you help me, I couldn't write. What am I going to write here? What's transfer function? What is transfer function? Output divided by
Yes,
input.
yes.
Okay, RS. Başkası yazıyor herhalde. Yapmayın çocuklar. Siz yazmayın. O CS over RS is equal GS over 1 plus GS HS. So you can easily derive that equation. Okay? You write the CS and then you obtain the BS, CS times HS, and then you can get CS over RS equal to this one. Okay? This is the transfer function. However, output neye eşit? What's the output? If you know the transfer function, so what you are actually doing here, instead of that one, you evet. I solved the problem. I solved the problem. System, that system becomes, again, oh, that system becomes like this. TF, transfer function, output CS. As long as you solve your control problem, you have RS input, RS input, and your transfer function here is equal to TF is equal to G over 1 plus GH. You are going to derive. If you cannot do it, I'll do it next week, okay? So you have to derive that equation. As long as you have a transfer function like this, it becomes like this. It becomes like that. It becomes like this. So that means obtaining transfer function is important for you in order to find the relationship between output and input. So your output then, efendim dinliyorum. Mahmut dinliyorum. Peki. I listen, Mahmut. So CS here, then you can calculate CS. CS is equal to TF transfer function times RS. Okay. So calculation of the transfer function is very important since it's going to easily give you the output value. I come back to original slide. As I told you, there are mechanical equations, either could be rotational or translational, and this is input output, multiple input, simple output, and this is output input relationship transfer function. And then what is BS? They asked. BS is the one which is equal to CS times HS. So ES is equal RS minus BS. So if you continue like this, you can obtain the transfer function. You derive it. You yourself do it. Try to do it. And for the closed loop system, CS over RS is your transfer function. Therefore, output is equal to this one. Transfer function times RS is going to be output, CS. Now, there's a problem. I just, for improve your knowledge, I just design a problem here. Say that if GS is equal 10 over S squared plus 2S plus 10, and if HS is equal to 5 over S plus 5, obtain the loop gain, GS, HS, and transfer function by using MATLAB, by the way. Today, probably you are going to, by doing by hand, and also you can use MATLAB as well, okay? You can improve yourself. These are the typical connection of the blocks. One of them is series connection. So this is the multiplication of those. That is the summation of those. This one is G1, G2. That one G1 plus G2. There's a question. No, you are going to put those in it. It's not very difficult to do that.
Professor, I don't understand. Do we have to derive each of like G of S and H of S separately and then multiply them together, or how is it done?
Just a moment. GS is equal to 10 S squared plus 2S plus 10, and HS is equal to 5 over S plus 5. So this is the control system. I'm going to use Can you see my pen?
Yes, we can.
GS is equal 10 over S squared plus 2S plus 10. HS is equal to this. And the control system is something like this. Can you see easily? Shall I make it wider? So this is RS.
It's clear, Professor.
It is
Yes.
clear, is it? Good. I'm good. So what you are going to do, transfer function is equal GS over 1 plus GS HS, which is equal 10 over S squared plus 2S plus 10 over 1 plus 10 over S squared plus 2S plus 10 times 5 over S plus 5. So you are going to solve that one. Then if you multiply both sides like this, it's going to be 10 over S squared plus 2S plus 10 plus 50 over S plus 5, which is equal to so multiply with S plus 5 to numerator and denominator. So S squared plus 2S plus 10 times 50. Değil mi? Payı paydayı çarptık. So the transfer function becomes 10, 50. So you are going to get 5 here. S plus 5 over, I'm sorry, is obtained. I did it by hand. So I expect you to understand how to write those functions in MATLAB and to make those calculations. Okay. So this is your transfer function. If you look at that transfer function, this equation has got two roots, S1 and S2. These are called poles. Poles. We are going to discuss it later in detail. However, you get used to. These are poles. However, S equal minus 5, SO equal minus 5 is your 0. This is 0. So numerator of the transfer function is called 0, and the denominator roots are called poles. Location of the poles and zeros are very important in your control journey, in your control design. Okay, so this is the initial point. Just I would like to manipulate some calculations together with you, and then I'm going to come back to my original system. Can you see, by the way, can you see my slide right now still?
No, no,
No, teacher.
You can't see it. I
no,
see.
no.
So,
Actually, we can. We can. If we change the screen, we can see the slides.
okay, do it then. So I would like to, my board, you can see my hand here. My board, I'm going to keep it like this in order to write equations and things like this easily. However, this is the main point. So if you look at this is the product, G1, G2. This is G1 plus G2. This one is obvious, G1 over 1 plus G1, G2, transfer function, closed loop, okay? This is, I mentioned that one. If you have two loops like this one is called inner loop, the other one is outer loop. What are you going to do? You are going to first solve this inner loop, get the transfer function of this one, get rid of that loop, then you solve the outer loop. Okay, don't forget that. Now that is very important part of it, of your design. So I'm going to, next hour, I'm going to take a break now. Let's come back. It's already, yeah, it's already 10 o'clock. So 15 past 10, okay. 15 dakika veriyorum. Kahve için dinlenin. But before you leave, I'm going to take attendance. Yunus Emre, Yusuf Amir, Right, Ozan, Muhammed, Mahmut, Halil, Hüseyin, Hilal, Hamza, Ali Umut. Bir dakika, ne oldu? Bir değişiklik oldu. Ben şunu kaydedeyim de kazaya kurban gitmeden. Tamam, kaydettim. Ahmet Fares, Ali Umut'tan sonra Ahmet Faez, Adil Bayraktar and Abdurrahman. Tamam. Yoklama. 15 past 10 o'clock.
Okay, Professor.
10:15. I'm going to keep, by the way, I'm going to keep recording on. I was told that if I interrupt it, it's going to be difficult for you. I don't know. So tell me which one is the best way to do that. So I keep recording now. I open the music.
Yeah, it's better if we keep recording.
Okay. No, it is not. It's my music. My course music, Vivaldi, Four Seasons. I prefer it. Evet, başlıyoruz çocuklar. Saatimiz, evet, bir dakikada geç gelmiş. That one is very important. This is a typical control system where you are going to learn and then become competent about the design of the control system, this part. Some electronic people call it amplifier, but I prefer to call it controller. This is actually controller. And if you look at that one here, this is your output. And of course, this is the plant. For example, an electric vehicle, that one, or an electronic network circuit. That is the actuation. Of course, if it is electric vehicle, that is electric motor, which is controlled by power electronics and things like this. But you define this controller is going to define your response. This might be a robot arm as well. So a plant is a robot arm, and that actuator is the electric motor to rotate it. And then you measure the sensor, you measure the output and see that it's not actually equal to the input. There is an error. Then you design an amplifier to do that. This is your job to design a controller here. Okay. There are a number of type of controllers. The simplest one is on-off control. On-off control is the one if, for example, room temperature, you are controlling the room temperature. Beni görmenizi istiyorum. Onun için kendime geçeceğim resim olarak. Now, probably you can see me. So assume that my room is going to be warming up. In order to warm up, in order to increase the temperature of my room, what we are going to do, we are going to give, for example, I have an electric heater here, and then turn it on, then hot air blow, then temperature goes up and up and up. When it reaches the wish of our, our calculation, then it turns off. Or if it becomes a bit higher than the required one, then it turns on. Then gradually my room temperature goes down, down, down, then becomes equal to the control system, and just slightly lower than this, it turns on again. This is what on-off control is all about. But that is the simplest control and also not sophisticated. However, these are the controllers you are going to use in your engineering life. Is the proportional controller, integral controller, proportional integral controller, PI, PD, proportional derivative controller, PID, which is the still widely used in control area, proportional integral and derivative controllers. But first of all, we have to complete the on-off control. That's a typical water level control. You can see that if that float, shamandıra we call it in Turkish, if that float reach a level, then of course the water here stop. If level goes down, then the solenoid valve change the position, and you can see that this is the water comes in but cannot get as long as this is here. But if you pull it upwards, this is electromagnet, by the way. Electromagnet is the one which moves the best electromagnet position. Okay, so probably you are learning now in your electromechanical energy conversion how electromechanical system or electromechanical energy conversion occurs. So this, but there's a spring here. As long as you put it off, then immediately spring pulls it or push it. Anyway, so the water gets in through that line. Anyway, so if it is on, that means your water, let's say, is coming, and then when it reaches a level, water becomes out. This is, of course, the output part as well, input and output. Okay. That is the maximum level. This might be a temperature as well. This is actuator actually. This is controller, by the way. Controller input is U. Yeterince büyük görünüyor mu? Buraya önem verin çocuklar. That controller input is E and output is U. So this is the transfer function of the controller actually. But if level is low, it turns on. If level becomes high, it turns off. Switch turns on when the level goes down the limit, and turns off when the level reaches above the limit. Generally, differential gap. There's a differential gap over there. Forget about that one for the time being. Now, this is a typical temperature rise. When this is a temperature, for example, and this is the time function, and the temperature of the room is getting up, up, up, and then there is a limit here, and there is another limit here. This is the maximum one. That is the one, the top one. Until temperature reach to that level, it's actually increases. But when it reach here, switch, the heating system turns off, and then the room gradually cool down, and then when it reaches to the minimum level, it turns on again. As long as it turns on, so the temperature goes up. As long as it turns off, temperature goes down. Okay, this is a typical system, on-off controller, and this is the differential gap between those. That is not very comfortable. For example, in a room, there's an homework. In order to keep the load current constant is a seriously connected RL load, which is supplied by a DC source battery, and on-off control is used through a semiconductor switch, MOSFET or IGBT, draw circuit model and derive the equations keep the current between Imax and Imin. Çözeyim size bunu. Birazcık şeyiniz, gerçi güç elektron dersinde you are going to learn it properly, but I'm going to solve it. Yeah, these are the controllers. Problem is this. Problem is this. We have a DC source, we have a semiconductor switch, and we have an inductance and resistance. Inductance, resistance, and DC source. But this one is a semiconductor switch.
Professor, the camera is tilted downwards a little bit.
Can you see it now?
Not fully.
All right.
Yes, it's good like that.
Okay. So this is the system. When the switch on, current is going to flow through that line. When this switch on, current is going to flow through that line. So let's write the equation now. The Kirchhoff loop minus Vd plus L di dt plus Ri is equal to 0. Switch is on, by the way, it's on. Then what's happening here is that Vd is equal L di dt plus Ri. I remember I solved this one for you, and you can see that either you are going to solve it ls plus r in S domain, is equal VDS over S, is a step function, or in time domain, I current is equal Vd over R steady state solution plus K times T over tau. That one is transient. So for time equals 0, current is equal to 0. So that means K is equal to, you help me, I couldn't find K here. If you put the initial value.
Professor, why did you add plus K times e to the power of negative T over tau?
This is the transient solution. When you either you are going to solve it in time domain or in S domain, you are going to come back to this equation. Okay?
Yeah, I mean in time domain, where did you get the K e to the power of negative T over tau from?
Well, if you solve that LR network, you can see that this part, you can see that part. When you solve this part, the solution is going to be transient. L di dt Ri equals 0 is a transient. So it is the function. If you store energy here, the function is something like this, exponentially decaying function when you solve this part. But for steady state, you have to divide by R. This is the steady state solution, and this is the transient solution. This you have to look at go back to your differential equation solutions. But in order to find the same result, you can use the S domain solution as well. By solving this one, you are going to obtain this one as well. Anyway, so if you write time equals 0 initial value and current equals 0, initially there is no current here, then you are going to obtain K is equal to, I couldn't write it, you help me to write. What's K here? Put time equals 0 here, exponential term becomes 1, e to power 0, 1. So Vd over R goes to the left-hand side, so it becomes minus Vd over R. From this one, current is equal to Vd over R, 1 minus e to power t over tau. By the way, tau here, tau, time constant. Who is going to tell me what's tau here? Time constant, which is L over R. Your circuit knowledge is weak. You have to improve that one. Although in power electronic course of mine, we are going to use those equations quite often, and you are going to be familiar with those as well. Tau is the time constant. So this is the differential equation. What's the curve of it? If time goes infinite, what happens? If time goes infinite, what's going to be the current equation is going to be? Can't you see that?
E to the power of negative infinity.
Yeah, you see, negative infinity becomes 0. So neglect that one. So it becomes Vd over R. So the waveform is going to be something like this. Time and current. Steady state value is going to be Vd over R. So that one is Vd over R, this value. But the waveform is going to be something like this. Okay? At the end, it's going to be this value. So steady state, time goes infinite, it's going to be, that is why the tau is called time constant. So it takes, if L becomes very high, then curve becomes very lazy. Current is not going to easily increase, since if L is high, that means you have to store more energy in your inductance. But this is not my topic right now. This is the solution. As long as it reaches to that value, so you would like to keep it. You would like to keep it in order to keep the current constant. Between those limits, that is the maximum current, this is the minimum current. So as long as this portion reached that one, to this part, then at this point the switch is off, then current is going to be reduced like this. Then for this part, when current becomes minimum level, it turns on, then turn off, turn on, turn off. So you keep the current constant between the I max and I minimum. You understand? So this is the typical on-off control of the current. I max, that one is I min. You can keep it in between those, turning on and off. This is what is going all about. So I would like to improve your some mathematical application of those as well. On-off control is not very good. We are not happy about that one. However, we have to improve our controller knowledge now. Industrial controllers. So the first industrial controller is minute. Probably you can see me now. All right. Time to time, I'm going to describe things with my hand and things like this. Now, this is the controller. Bu controller'ın ne olduğuna bir bakalım. Let's have a look at what is this one. Probably this is your controller. That is the one. So this input is error, but this one is the output of the actuator of the controller. Okay. Now proportional controller. I'm sorry. This one is the input of the controller. That one is the output of the controller. So if you amplify it with the constant value, Kp is the adjustable proportional gain. So this is called proportional controller. Okay, this is a proportionality constant, Kp. Did you understand that one? So we are actually multiplying the error. We are an actuator multiplying the error and sending it to the actuator. This is controller. This is the first one. Second one, the error is also integrated. If you integrate the error and multiply with the KD, KI, I'm sorry, I couldn't see properly. Biraz büyüteyim. That's right. KI. So that means integral constant, and the control action is called integral control action. So I repeat, your controller output is actually integrating the input, error input, error, not input, error input. Always integrating it. What does integration mean? I have a question. What does integration mean? Integration actually is getting the summation of those. So you accumulate plus, plus, plus, plus, plus. So integration means that you are actually accumulating the error. And in S domain, of course, is K over S. Integral constant over S is the transfer function of the controller for integral controller. I'm rather skeptical whether you are following me. Tam emin olamıyorum. Benle birlikte mi geliyorsunuz? Takip edebiliyor musunuz? That one is the proportional constant. You can see that this is the in S domain transfer function of the proportional gain. That one is the integral gain. Of course, you can adjust that one by changing that constant here. Okay. What about derivative controller? First of all, before than that, proportional plus integral. So the proportional we have already discussed, plus integral we have already discussed. So altogether, it becomes proportional plus integral. This means evet, içine giremedim. Bir dakika. Yeah, that's right. Or still which is equal to Kp plus Ki over S Es. Ya bunu ben sevmedim bu işi ya. Bir dakika. Siz buradan anlayamayacaksınız bunu. Tamam. Just a moment please. I come back. Proportional controller is Kp. Okay. So for proportional controller, actually US is equal to Kp times Es. from this one. Tamam. For integral, however, US her seferinde kalemi açmak gerekiyor. For US is equal Ki over S times ES. Okay? From this equation. Now, for the combination of those, that one, I'm just writing here, US is equal to Kp plus Ki over S times ES. We already have derived those. Now, if you employ Ti, Kp over Kt, I just come down here. So if you get the Kp from this equation, if you write that one here as equal to Kp bracket 1 plus Kp Ki, sorry, Ki over S times I'm sorry, I made a mistake. Who is going to correct my mistake? Who is going to correct my mistake? It was going to be 1 over Kp. One over Kp Ki over S times ES. Şöyle kapatalım. ES. From that equation, if you define Kp over Ki, then you obtain this one. US over ES is equal to this. This is proportional and integral action. This is the equation we have. All right? Buraya kadar tamam mıyız? Are you happy with that one? Did you understand what we have done? What we have done, first we have, this is a proportional constant, so US is equal KPES. For that one, which is Ki over SES, therefore, if it is there, two of them together, proportional plus integral, then you obtain this equation, Kp plus Ki over S. If you get the Kp bracket, of course, there is no Kp here, so 1 over Kp should be involving. This is 1, of course. And Ki over S is already there. Therefore, when you define Ti is equal Kp over Ki, then of course you take that Ki derivative of the denominator and you obtain this equation, the red one, the red covered equation. Now let's go back. Let's move for derivative action. Sorry. Derivative action is not given directly, but what is here, that one is the derivative action. So that means you are actually multiplying with S. Kp times Es, proportionally is over there. Et, of course, Kp times Es. But for that one, Kd times, now derivation, what are we going to do? Ne demekti derivation in S domain? Are you sure that you are there? Are you sure that you are following my lecture? If that one is, there is a derivation here, Adel, tell me, in S domain, what derivation means? What are you going to add? Either multiply with S or divided by S. Which one for derivation?
We're gonna multiply S.
Not multiply with S. Thank you. Thank you very much. So what are we going to do? We are going to write in S domain here. So I'm going to write here US is equal to Kp plus Kd times S Es. So I converted this time domain equation with in Laplace, apply Laplace form, and then convert it to S domain. So this one is Kp times Es, this one, this term, the first term is equal to, this first term is equal to Kp times Es. The other one is Kd derivative action constant times S, Es. Therefore, when you solve it and get the bracket of Kp, then what you are going to get, ut is equal to Kp et plus Kp times Td det dt. So you call it Td is the derivative time. So you Kd over Kp is equal to this Td. Then you obtain this equation. Tamam mı çocuklar? Tamam mı? Yani şu benim yazdığımda KP parantezi, if you get a KP bracket, KP parantezini alırsanız, KP parantez 1 plus KD over KP gelir buraya. KD over KP, which is equal TD. TD is the definition here. KD over KP. Then you obtain this equation. KP bracket 1 plus TD over S. This is the derivation. US over ES. Now, if three of them are together, that one is proportional constant, that one is integral constant or integral action, that one is derivative action. Three of them together, when you put it as KP here, for this one KI over S, for that one is KD times S, and then the continuous similar TI and TDS, similar what we have done before here. We have done it here. You can see that 1 plus TDS and also 1 over TDS, TIS here. When you put those together, you are going to solve the system. You are going to obtain this one, KP bracket 1 plus 1 over TIS and plus TDS. Then, of course, if you divided both sides TIS, then you obtain KP 1 plus TIS, 1 plus TI TDS square and 1 TIS. Bu biraz büyüteceğim. That one is worth to discuss. If you have a PID controller, you are actually what you are doing, what your controller is doing. Probably you may not answer this question first. So I come back and start from single ones. What your controller is doing here is just multiplying with a constant. So amplifying it. What your system is doing here so there is a S in denominator. So dividing by S. However, here together, altogether, if you look at the red one, please. Red one, please. So your controller actually now adding a constant, but also 1 over S, adding 1 over S here. Okay. For derivative, you multiply with S. But altogether, three of them together, you obtain that one. Now you can interpret that one. This is the transfer function of your controller. What kind of transfer function is this? Follow me carefully. You are going to, this is going to be open up your mind immediately. This is a controller, by the way. This is the controller. This is the one. Yeah, this is the one here. That one here, controller. Your controller is something like this equation. Your controller is that type. Now, what's happening here? This is a second order system. So it has S01. Tamam, alacaksın. Break vereceğiz. S0 2. We have two zeros. You are actually adding two zeros to the system and one pole. S pole. You are actually adding two zeros to the system and you are actually adding one pole to this system. This is what PID is doing that. I hope you understand that. I'm going to start from this point. Okay, we are going to take a break. 11:15. Okay, 11:15. Okay. So we are going to continue at 11:15. By the way, my assistant hasn't come yet. Okay, I take a break. You can now get a coffee, tea, whatever, or eat something. Evet, başlıyoruz tekrar. We start again. For controller, which you are going to design those values, you are going to select, for example, the KP value. You are going to select the TI and TD values in order to obtain the best performance of it. So these controllers are important. What we are actually doing, the derivative action, we are getting the derivation of the error. For integral action, we are getting cumulation of the error. So both are acting properly. Particularly the integral is very good for reducing the steady state error. Now, if you have a closed loop system like this, and if you have a disturbance, what are we going to do? I have a question. Do you have any suggestion? You have to combine the last week knowledge with this one. You are going to ask this question, whether this system is linear or not. If system is linear, then of course you can use superposition theorem. So you can assume that you haven't got any disturbance, and then get the transfer function for this input. And then the second step, you assume that you only have disturbance and you haven't got any RS here. Then solve it, and at the end, the final solution is the output of the first one and the second one. Did you understand? Now, let's have a look. The first one, CRS over RS. I come back. So we neglect disturbance. There is no disturbance. So the differential transfer function of this one is equal to G1 times G2 over 1 plus G1 G2 H. Buraya yazayım bir. Sonradan gelenler var. For the first one, TF for R is equal to G1 G2 Okay, baştan başlıyorum. I start. Transfer function of this one for only RS, D is equal to 0. So transfer function is this one, TF for R is equal to G1, G2 over 1 plus G1, G2, H. Do you agree with me? G1, G2, there is no disturbance. 1 plus G1, G2, H. For disturbance only, if you have a disturbance only, I'm going to show it in blue color. There is no RS. This is the input. So that is the output. And this one is the feedback line. Feedback line here. So that means if I write the equation here, G2 over 1 plus G2, then H, then G1 is equal to transfer function D. So for blue case, we assume that we only have D, but we haven't got input. And for the red one, then in that case we haven't got D, and we obtain transfer function. So if I come back here, I already obtained those transfer functions. The CRS over RS is equal to, as I derive those equations, G1, G2 over 1 plus G1, G2, H. CDS over DS is equal G2, 1 plus G1, G2, H. One thing is interesting. We need to find the final solution. CS, the output, is equal CRS plus CDS. CRS is equal to this. You have to multiply with RS. CDS, you have to multiply with DS. So at the end, we obtain CS is equal G2 over you get this G2 bracket, G2S over 1 plus G1, G2H, G1S times RS plus DS. Tamam mı? Anladınız mı? We employ the superposition theorem. Okay? Now, the comments. Feedback reduces the disturbance effect. Of course, disturbance is here, and the disturbance effect is reduced with the feedback. This is the first one. The second point, the comment, feedback reduces the sensitivity to parameter variation of G1, G2. Of course, you don't know how sensitivity is all about. Therefore, I'm not going to mention that one to you. But sensitivity means your networks or your control systems dependency of the parameter variations. Evet, bakalım nereye geldik. Evet. Bunu derive ettik biz zaten. We have already driven. Can you solve this differential equation for me? Can you solve it for this electric network? And can you obtain this line, this or block diagram? So that means establishing a block diagram. Can you do that? Pekala. I know your circuit concept needs to be supported. So I go back to my second camera. Now the circuit, yes, you can see, but you can't. Can you see right now?
Yes, Professor.
Okay. So that is the network. EO output, EI input. Okay. Resistance and C. One equation is this. Current here current E, I. The first equation is equal to IT is equal to EI minus EO over R. Of course, we know that. What about the second equation? You have the capacitor and the voltage here. The I is equal C dV dt, or which is equal C times dEO time function dt. From this one, EO is equal 1 over C integral IT dt. So one equation here is this. The other equation is this. So if you look at S domain, in S domain, that one is equal EI S minus EOS over R. That one. This one is EOS is equal CS. So we have already derived those equations. This is IS. by the way. And the EOS equal to IS over CS, then in order to represent the case in so if you come back to my slide, the first step, EI minus EO over R is equal current. Then current times 1 over CS is equal EO. So that is the feedback you derive by writing those equations. I have already written those equations in order to improve your understanding of the topic. So that means block diagram could be derived. That is the block diagram of this electronic circuit or electric circuit. That is generally it was very popular in past to make reduction in the calculation of the or solving the block diagrams which is rather complex. If I come back to multi-loop, you remember that I said first you have to solve this loop, then the second loop comes. But sometimes, as it is in the problem I'm going to show you, you have to get rid of those loops. That's the one. I amplify it. You can see that there's a problem here. What are we going to do? We need to find this form. So simple block diagram in input and output, that is the transfer function. But we need to know, we need to find that one. First of all, we have to get rid of this complex system. What we could do, by the way, since this loop, there is a loop here, is also crossing the loop here. So we have to shift one of the loops. We are shifting this loop. We are shifting this loop. Biraz küçülteyim. You can see that anyway. So we are bringing that loop to here. What kind of error if directly put it here? So then later it's going to be multiplied with G1, which it shouldn't be multiplied. So if I decide to divide this H2 divide by G1, then it's all right. You can do that. Since when it is multiplied with G1, you can get rid of that one. The first action we do, okay? We bring it here. So this is the first thing we have done. First step. We get rid of that one. Then it becomes simple. As long as you get rid of that one, this is equal to G1, G2 over 1 plus G1, G2, H1. Bakalım öyle mi? Let's have a look. Oh yes, it is. G1, G2, that one here is the loop is G1, G2 over 1 minus, by the way, this sign is plus, therefore it should be minus 1 minus G1, G2, H1, okay? Then it becomes simple since you can multiply with G3, and then you can solve this feedback easily. When you do that, you obtain, oh yes, you obtain this one. G1, G2, G3 over 1 minus G1, G2, H1 plus G2, G3, H2. Nerede o? Şimdi if you multiply with this one, with that one, you obtain that one. You should do that. Okay? You, as I told you, you are going to think all the time. So you are going to spend some time beyond my 3-hour course. Of course, in general, the distance teaching hours are reduced, but I certainly be sure that you have to follow me as if I'm in the classroom, okay? When you solve this, when you solve it, you easily obtain this transfer function. Of course, it is G1, G2, 1 minus this one here, and you can put this one also is a plus. The state space method is completely different approach. Completely different approach. It is time domain equation, and the state of the system is set of variables such that knowledge of these variables and the input functions will, with the equation describing the dynamics, provide the future state, and system is called state variables. Some advanced control problems are solved with state space method, but first of all, you have to understand the proper as a normal domain system. I'm not going to get in right now, state space systems. What we have learned today is the application of the superposition theorem to multiple input control systems to reduce the complex feedback systems, to reduce the level of it. We already have done that. And also we have learned that what proportional controller is all about, what integral controller is all about, what derivative controller is all about, and what PID, proportional, integral, and derivative controller is all about. That means with adding a controller to your control system, you are actually adding 2 zeros and 1 pole to this system. 2 zeros and 1 pole you are adding. So I go back and look what we have done so far. On-off control is of course widely used, but not a very good, not comfortable. For example, in your room, now you would like to want your room temperature should be 22, okay? But you fix it maximum level 24, minimum level 21. So when you blow up and warm up, so it reaches to 23, then you feel all right, it's hot. Then switch turn off, gradually reduce this temperature. Of course, it reduced to 22 as well. But then further reduction until 21. When it reaches to 21, you feel that, oh, that's bad. I feel cold. You feel hot, you feel cold, and then of course that is not very comfortable control system, or not very accurate actually. So controlling the temperature between 23 and 21. If assume that you are going to reduce the maximum minimum limit, then it's going to be then turning on, turning off, turning on, turning off. So you are going to switching on and switching off. Frequency is going to be increased. So that's why on-off controller is cheap, however widely used. However, it's not comfortable. It's not very accurate either. Yeah, we have derived those equation as well. Okay. Okay, I'm complete. I have completed my session. So follow my OLearn system. I might drop home assignment, and also I'm going to upload this to our system as well. Okay. Is there any question that you are going to ask? I'm sorry. Okay, then I close up the classroom. Thank you for attending. Okay. Bye bye all.
Hocam, don't close it. We have a lab now.
Anlamadım.
Lab'a başlayalım hocam. Şeyi kapatmayalım sesini.
Bir dakika. Şey orada mı? Bir dakika. Ha, Muhammed oradasın. Tamam. Don't leave.
Ders sonunda
You
ben
are
kapatayım
going to-
hocam sesini.
Tamam. Kayıtta dursun o zaman Muhammed. Tamam
Tamamdır
mı
hocam.
evlat?
Hı.
Okey.
Tamamdır hocam.
Hadi bol şans.
Teşekkürler hocam. Hello everybody. Don't leave, okay? Don't go anywhere. We still have a lab now. Let's share screen. All right, can you see my screen right now?
Yes.
Is it okay? Yep. Okay, now everyone has the MATLAB. Did you install it? It doesn't matter, like just download the last one. It's okay, 2018, 19, 20. It's okay, it's all versions are okay. So let's run our MATLAB. Let's start it. Okay, so guys, is everyone here? Just comment yes in the section, all right? I want everyone to follow. So we have 17 students here. All right, 1, 2, 3, okay. Come on, guys, I want everyone here. We're gonna start now. Still a lot of students missing. All right, all right. Okay, then let's start. So you can like start with your MATLAB in a partial screen like this on the right side and your web browser on the left. You know, you can watch screen on the left and type your command on the right side, or however you want. I will go with MATLAB. Let's start it here. Here we have a command window. We have our current folder, and we have a workspace. All right, this is the MATLAB like default setups. Now, how many students are here? Let's see. Everyone follows, guys. We have 17 students, only a few of them here. 6, 7. All right. Okay, let's keep. Can you hear me right? And see my MATLAB screen? Just write yes or no. All right. Okay, let's have a start. In MATLAB, we have a like command window. We're gonna use this one, and we have our current folder. We can see on the left side, and the details about our file will be on the left down. And here our workspace, our variable was defined in here. Let's start as a define x equals, let's say from 1 to 10, all right? 1 to 10. You see when you hit enter, it will give you x equals from 1 to 10, right? And you can see your x variable in the workspace on the right side. And then let's say y equals to square root of x, right? SQRT and open parentheses and write x, hit enter, and it will give you square root of x, all right? And then you can plot this variables. You know, you can write plot open parentheses x comma y. Just hit enter, and then you get the like plot of x and y. And then you close it. Let's say you want to execute a lot of commands at multiple times, you know. For this, we're going to use a live script, you know, here. You can hit new and live script. In live script, you can write your codes like line by line without executing them. And also here, you can like come to the command window, hit the up arrow, and then you come here, you come click the dock, and you can see your command history here. Let's say we execute x, y, right? We give them variables. Then you can press Control and hit choose these ones. Then hit right, copy, or you can just hit right and create live script. It will just transfer it to the live script, right? Not this one. See, and then you can take it from history to your live script, and then you can keep going it, writing it like here. But you need to add parentheses here. It's not like the command window. Then you can hit the run. Hold up, someone has last one. All right, let's repeat it again. Here you came here, right? On your command window, you hit the up arrow, okay? Up arrow. And there is a command window. Let's say, where is it? You press the up arrow, and there's a history, right? History of commands. You press this arrow and came to dock, and it's separated on the right downside, all right? And then you can hit press the Control and then choose these variables that you want to transfer it to the live editor, and then hit the right click it and create live script, right? You just transfer your the codes that you write in the command window to the live script, right? And then here you need to add dot comma at the end of them because it will not execute one by one. So like this one. Doc comment, just separate it to the another one, you know. Where is it? You separate the comment window to here. You can see your comment history. If you want to go back to default, you just here, there's a layout from the home section to layout. You can here press default. It will just go back to the default settings, you know. It's okay. The doc doesn't matter right now. Let's say we just want to create something else. You can write it like a equals 5, b equals like 7, and then you can create like c equals to a times b, like say, or you can display, let's say, wherever you want, lol, but you need to add this comma here. Then you can hit the right live editor and then run it. You can write, you see there's your variables are defined on the workspace right side, right? And when you hit the display after this execution of the codes, it will display the message that you write here, right? It say LOL, doesn't matter. Like you can change the view of the live script. Your variables, your answers can be under the line of the code, or it can be on the side, right? Or you can see only the results, or they can be on the right side. See, can you hear me now? Can you hear me, guys?
Yes.
Yeah, it's okay. Okay. So fast. Okay, let's slow down. Write something. I cannot hear you. You're not giving any reaction, so I have to go normally. No, guys, you can open your microphone and talk to me. You can talk. So I'm on the application side, so you can open your mic and talk to me right now.
Yeah, please
Let's say
try
we
to go
create
slower.
slow. Okay, let's slow down. Now you can write attend variable here and display a message after it, all right, in a live script. Let's say here we have a section comments, you know, say percentage, right? This percentage, you can explain your code. I say, what are we doing? Say type a percent, right? Start typing, right? Let's say this one is explain the like code. Let's say, what are you doing in this code? It's a like comment, all right? You can organize your code by the sections, which is, let's say you type 2% and hit the space, and then let's say new section. Then you hit the enter, it will separate it to other section, and you can run the codes section by section, not all together, but section by section, and then you can see the results. All right. Let's say what are we doing? X equals to from 1 to 100. Y equals to from 101 to 200, let's say. Then plot this x, y. Let's say after you write your code, you can hit the run section here. It will only execute this section, it's not going to execute the other section, all right? And you can see your result on the right side. But everyone okay till now? So far so good? Guys, are you here? Yes, right. You can answer with your microphone too. Don't forget. And then we have indexing. We use indexing to take a subset of a vector or matrix. Let's say here, or your x variable, like y variable. The fifth element of y, we see here is 105, right? You can from the comment window, you can like, let's say y5, the fifth element of the y, right? Hit enter, it will give you the answer, right? 105. Or you can, like, say the eighth element of the y. What is it? It's 108. See, it's 108, right? You see. And then let's say you can attend a variable to this one. Like, let's say we have a v equals to the fifth element of the y, right? And then here in the workspace, you see v equals to 105, right? Fifth element of the y. What else? You can change the first 5 value of the y to be the like 6 to 10. Let's say y from 1 to 5, all right? We can change this variable. Let's say equals to, you can open, come on, say 6, 7, 8, 9, 10, all right? Hit enter, it will change it, right? You see the first from 1 to 5, see 6, 7, 8, 9, 10. We can change the variable by this way. And then let's go back to do our live script. And then there's a if else, if else section. Let's say user input equals to input. Say you can ask the user to input something, right? Let's say, did you learn something? Right? And ask a question, yes or no. And press the S for the streaming. Right? When you write this, let's say run the section, it will ask you, did you learn something? Or you can press Y, right? So let's under this one, let's define if the user input like user in, say equals to n. Let's say if the user input the n, let's say, did you learn something? No. What we're gonna say, we can like display oh man, you didn't learn anything. Or you can add the else section, right? If the user hit the n, you can display this message. Or else if, let's say else if they press something else, then you can like this user in equals to, let's say n, say hit something else. You can display a message again and then say, please reread again. Give the message again here. And then you can hit else if the user input something else. Let's see. For the else, you can add it. let's say user input n. I mean, we can ask like why you did type this. You type n. And then don't forget to at the end. In if and end, if else, there's only can be one if and else, and you get multiple else if function here. Let's say you can ask else if the user input q. So you can change your q. You can else if, let's say, user in equals to what, let's say something else, w. You can add multiple else ifs here, and then you can display a message here like this one. Let's say on type w. You can and then send a message to that. Like, so you hit the run the section, and then it asks you to run the section. It will ask you to learn something. Let's say hit enter, yes. Guys, everyone following? Are you here?
Yes.
Yeah, all right. Okay. Let's say you can save your file here, all right? You coming to here, save as, let's say, the MATLAB. You can save it like here, and then when you click it, you can see on the left side current folder. And then here command window, you can clear your command window with the clear, and then it will clean your workspace. You can hit the CLC, it will clear your command window. Let's close this one and go back to the home. There's a plot apps, and here in app section you can use a lot of apps. That depends on your project, which one you want to use. But first important one here, Simulink. We're going to use Simulink in our lecture. First, you need to learn Simulink very well. Let's start the Simulink. Here in the Simulink, we're going to use here blank model. You can hit the create model. And then here are our Simulink model, right? We have our browser, library browser here. We're going to choose the things that we need from the library. Let's say here in control system, we are using transfer functions, right? You hit your transfer function, right? And you can see here discrete transfer function, zero pole, but we're gonna use here down here discrete time. Where is it? Here, discrete function with initial outputs or initial states. You can use one of them. So here, this is your transfer function. When you double hit it, like your numerator and denominator, you can change it. Like say, you can change numerator to 2, and then denominator, let's say it's 5s plus 2. We can change it to 5 to 2, and then apply it. Okay, you save it, and then here we need something else for the, like say we're creating a loop, all right? You need a what? You need a gain also. Here are the gain. You choose gain and you drag it on the worksheet. It will come up here, right? And then for the transfers, you need a sum, say sum here for the connected transfer to each other, right? Let's say we need another transfer function. You just Control C, you copy it and paste it, and you get another one. here are the, you press this arrow, all right, and then you can connect it to wherever you want it to go. Here are the gain. You know, gain is output over input, right? So you get you get from the output. Let's say connect these two transfer functions here, and add a divide. Say divide product, all right? We need divide, right? Let's say we connect this transfer function, you divide it, you connect it, and then you get your gain from here. So you get from gain from the output, and you want to connect to the to here input. You can double click here, and then you can change it. It's gonna be sum or deviation? Like you can you check it, change both to the minus, all right, and then both will be deviation, and then you can change it to like, let's say 1 plus 1 minus, all right, and then you can change it. Here are your transfer function. You can change your transfer function numerator and denominator. And then gain, you can decide your gain value. Let's say it can be 1, 0.5 or 0.02. And here are division. Your division, you can change it like this. You can decide both can be division, both can be multiplication. It's up to you. It's up to your function, transfer function. And then here, let's say we need an input. You need input. Where's your input here? All right. You get your input here. You can decide attend a variable, your input. When you double click it, you can see your block parameter here. And then there's an scope, you know, for seeing the function, you need a scope. The scope will show you the wave, right? Let's say you connect your output to the scope. And then here you need another input. Let's say you can just copy this, and then you can connect this to. See here, your transfer function, you attend your numerator, denominator, you can change it from here. You attend the gain here, your sum product here, you attend an inputs, and then you transfer it, and then you get the scope, right? You can just hit the end, run, and it will run your function. You can see the results here. Double click the scope. Yeah. Right, guys, so far so good.
Yes.
Name of the input. Name of the input. You can change the name, right? Let's say wherever your system is, you can say it can be voltage. You decide it and attend it. You can change the name by this by double clicking here. You can change the name. Let's say it's actuator. This one is actuator. Let's say this one is engine. It depends on your function. Let's say this one is engine. I mean the circle after the first input. Circle. This one is sum product. You know, you get your input, you get your gain, and then you add it to the function. This one is a sum product. You know, here it can be, you can add your gain or don't add it, right? Both can be minus, both can be plus. You can add both to the system. All right, it's a sum product. Sum product. You see it in the lecture, right? Your function need this to transfer the function, connect the function together. All right. Okay, guys, you understand?
Yes, hocam.
That's it for today. And next week we are gonna start the experiment. It was just the entry. You can look in internet for this Simulink. There's a lot of documentation about MATLAB, but the most important thing in here, you can just hit the like a question mark here, right? You just click it and you can find documentation about any topic. The MATLAB has an awesome documentation. You can use it. Just this one right here is the most important one. All right, don't forget. You just hit it. It's open MATLAB documentation. You can just find every topic you want to work on. All right. So next week I'll see you guys and we start our lab. All right. But
All right.
don't forget transfer functions. We're gonna start lab. So take a look to the transfer function, the sum product. All right. See you next week.
See you hocam.